Good afternoon, everyone, and welcome to today's eSeminar, Power of SIMULIA Portfolio 6, Journey from Validate to Innovate. So I'm going to introduce today's presenter, David Barnes. He's the Senior Director with SIMULIA Growth Initiative, and he graduated from University of Pittsburgh in 1983, and he spent 8 years at what is now Rolls-Royce performing simulation as part of the Advanced Engine Design team, and another 8 years pioneering simulation methods for General Motors lighting products before joining AC Engineering in 1999. Many name changes and a few acquisitions later, he's now responsible for leading a SIMULIA special initiative to guide customers along the journey from Validate to Innovate by leveraging the SIMULIA power of the portfolio. Before taking on his current role, he's performed consulting, managed the engineering services, has served as GM for the SIMULIA central offices, and for the past 7 years has directed the Americas field organization for SIMULIA. So with that, I'm going to give it over to David.
Great. Thank you, Katie, for the introduction. Appreciate that, and thank you, everybody, for joining in. Look forward to spending some time here together. I'm going to try to make it light and enjoyable, so I'll start out with just a little bit of trivia, a pop quiz. Just wondering if anybody recognizes this gentleman. I would be very surprised. So let me give you a little bit of a hint. This is the same gentleman, and now we have a little bit of context. You might have figured this out. The setting is 1997, and a very significant match between Garry Kasparov, the then world chess champion, and IBM's Deep Blue computer. And to me, this was a very significant event because, as many of you know or could guess, the outcome of that was that for the first time in history, a computer defeated a chess world champion in tournament play. And so, what that really meant to the computing world was that we now had a new respect for the power of the computer. Up to then, everybody understood that computers were good at math and they could do repetitive tasks, but I don't think many people gave the computer credit for being able to accomplish things that required any form of creativity or thinking. And I think this event really kind of changed the mindset of a lot of people in that regard. But I'd really like to give IBM a little bit more credit than what the documentary did that was entitled Man versus Machine, because in truth I see the IBM side of this, or the Deep Blue side of this, as a very strong collaboration between the IBM programming crew and the hardware team. So this is really, I think, a better phrase would be man and machine. Today we have examples everywhere of the computer doing very creative, very powerful things for us, from planning and executing surgeries in the operating room to using our handheld devices that we have with us at all the time to find the best route from New York City to Los Angeles in a matter of seconds, finding the best route from among the millions of possible routes. And I think we're already prepared for the fact that soon we'll have vehicles driven by computers, and no doubt they'll actually be doing a much better job from a safety standpoint than what humans can. And so we see these examples everywhere that we look. But what I really want to focus on today is how can we tap into that same power in helping us to design products. So let me start with taking stock of what our current simulation and design process is, what we're normally accustomed to is taking a design, using our finite element analysis tools to interrogate the performance of that design given different various loads and boundary conditions that it's exposed to. And so that's great. That uses the computer. I think we really are leveraging a lot of power in order to do that. But that's really just validating a design. The key question that we all need to really ask is, where did that design come from? And so that takes me back to Garry Kasparov. I opened up talking about the chess match because I think the challenges that a product designer faces are very, very similar to somebody playing chess at a very high level. Basically, in a chess game, you at every move have to take stock of every option you have available, and you have to try to imagine multiple moves ahead and how your decisions are going to impact the outcome of the game way down the road. Well, a product designer has really kind of a similar process that they have to wade through. They have to take stock of all of the design variables that they have, all the knobs they can turn to develop a design. And they have to think about all of the operating conditions that that product is going to be exposed to in use, both use and abuse. And they also have to consider manufacturability, cost, weight, stiffness, all these different qualities. They have to try to keep all of that in their mind while they're developing this design and try to imagine how their choices impact the ultimate performance and quality of that part. So it's very similar to what the chess player has to juggle in his mind. And really on the part of the designer, what makes that particularly difficult is that a lot of those objectives directly compete with one another. Classic example is weight and stress. As you try to reduce the weight, try to minimize the mass of the part, you increase stress, you are fighting against the durability and reliability of the part. So these competing objectives make it particularly difficult. So what happens is that the average designer, like the average chess player, focuses on just a very small subset of the possibilities and basically develops their design based on that, and they hope for the best. That is really the process today, and in order to really manage that process, what designers invariably do is they stick to variations of an existing design, and that is not innovation. That is a slow evolutionary process of evolving a design. To really innovate, you have to be able to get beyond just variations of a design. We want to be able to come up with radically new concepts, but yet we still have to have confidence that we've considered all of the possible loading conditions and all of the objectives of the design. We have to be able to have a confidence that we've considered all of those things, and that's where the computer really becomes necessary. And so that is exactly the concept that I'm trying to outline here today in this presentation is the process where we can tap into the computer and use its tireless, exhaustive approach to looking under every stone and considering every option, that same power that allowed IBM's Deep Blue computer to beat Garry Kasparov, the brute force method, we want to use that to help us develop these innovative, novel designs. And just to give you a flavor of how some of our customers have already been doing that, one of my favorite quotes comes from Jeff Williams in this SIMULIA magazine article, where Jeff talks about developing a new cone for their downhole expandable product line. And Jeff uses Abaqus and Isight together, and the quote that is really pertinent is where he says, if we hadn't been using the software, the most effective cone geometry would have never been considered. And so I think that is pointing to the traditional process of looking only at incremental variations of a design, a subset of the possibilities, and missing the big, innovative, new idea. And because at Baker Hughes, Jeff, relied on Isight and Abaqus working together to explore the entire design space, they were able to find this novel new approach to a cone. Very similar idea was presented in the 2014 SIMULIA Customer Conference. It was a fun presentation given by Dan Price, and he talked about developing the spring blade shoe at Adidas. And his point was that the number of combinations of tread geometry and materials and thicknesses and just all of the possible parameters that would be in a design study were just not manageable by hand, and that really only by employing the power of the computer were they able to guide through the myriad of options and find the robust combination of all of these parameters that led to them introducing the very successful spring blade shoe. And this year in the conference that was just a few weeks ago in Boston, I hope some of you attended that, you saw Jay Moss from Trek Bicycle talk about how they have been very dependent on using the power of the computer to explore many different parameters to be able to bring industry-leading bicycle designs to the market. So there are a number of great examples in the conference proceedings and in papers that our customers have presented that really point to the fact that many are already taking strong advantage of the computer and doing more than validation. They're actually using the computer to help them find and arrive at new designs. There are a number of foundational pieces that you have to have in place in order to really be able to do this. And the first and probably most obvious of those is to have high-performance hardware and software. Well, Moore's Law has, continues to hold true to this day, so that in 1997, the computer technology that existed at that time that allowed Deep Blue to beat Garry Kasparov was a fraction of the power that we have on our desktop today. And so, we continue to get better and better hardware, and we can take advantage of that year after year. And in terms of software, SIMULIA every year releases new versions of their products that have been optimized to take advantage of those hardware advances. We also have to have accurate physics, and that is really what's embodied in our Abaqus product. I think that for 38 years we've been developing Abaqus. It's recognized as a leader in providing realistic simulation, and that's again somewhat of a given that would be a foundational piece of this whole process. But some of the lesser known or maybe appreciated parts of this whole puzzle are that we need to have tools for process automation, which allows many designs to be assessed automatically so that the computer can work around the clock and without needing manual intervention. It can just grind away and tirelessly search for design options. And that also then relies on a tool, something that will be able to integrate all the pieces that are included in that design process. So I'm talking about your CAD package, your simulation package, any third-party applications that you might be using. Maybe you have in-house codes. Those all have to be coupled together, and so you have to have unique tools to be able to integrate all of that so that it can be automated. And we also have to have process guidance and decision support so that during the design process, during this automated process, there is intelligence embedded there that will make sure that you're moving towards a better design, or that you can at least tease out which of all of those that you've looked at are really the best designs given all of the various load conditions, operating conditions, etc. And finally, we do need a method to manage the volume of data that's produced as a result of this. But even more importantly, and maybe less obviously, we need to have specialized tools to allow us to post-process across many, many data sets so that we can look at the dozens or hundreds of design variations that we've considered to make sure we can quickly and efficiently pick out which of those is the best design. Well, over the past number of years, Dassault Systemes has acquired, assembled, developed, brought all of these pieces together into the portfolio of products that we have today. That consists of Abaqus, Isight, Tosca, FE-Safe, Simpo, and Simpac. And we're also bringing all of those products, all of those technologies together into a common user interface in our 3D Experience platform, new generation of products. So all of these pieces are available to our customers. And what I'd like to do now is share with you a good illustration of innovation, an innovative design process in the works. And so I'm going to show a video, and we will really interrogate what we saw at the conclusion. Now, for those of you that that maybe was a little bit choppy, don't worry, we will be posting a link to that video on the learning community, and so you'll have an opportunity to watch that at your convenience again. So apologize if it was choppy at all for you. But what I'd like to do now is talk through many of the steps that you saw in the video. Really, we want to talk about the steps, kind of chronological steps in the development of this novel brake rotor design that was shown in the video. But the first thing that we're going to talk about is something that's really common to both the validation and innovation modes of product design. And I think that's really the realistic simulation part of the puzzle, Abaqus basically. So we know that no matter what, whether this is a validation mode or we're in the middle of innovation, we're using Abaqus for the physics behind everything. And so we're using Abaqus to essentially study the heat transfer, looking at the cooling, all of the brake force, the loading. We're looking at all of these different aspects of the design, simulating the performance. But then we're also studying things like the warranty. We want to understand the warranty exposure that we have with this design. We want to look at weight and cost. We want to look at the manufacturability of this. We have all of these features that we want to study, and we can do all of that manually. But what we really want to be able to do is look at all of these aspects of the design quickly enough that we can pour through many, many designs searching for that best design, and that means we really have to begin to look at automated processes and other ways of getting through designs very, very quickly and efficiently. So we'll be looking at using Abaqus as the foundation of the physics, and we're going to look at Abaqus and Friends to try to improve the throughput of the simulation. In the video, we've actually made good use of the products Abaqus for the physics, Isight for process automation, process integration, and parametric optimization. Also FE-Safe for the durability calculations to make sure that we have a robust product that will serve the intended use. And we'll also explore how we use Tosca for topological and shape optimization as well. So those 4 products are going to be highlighted here, and they're special in another sense because if you have extended packaging, you already have access to all of those products. So Abaqus, Isight, Tosca, and FE-Safe all draw on the same interactive token or compute tokens for solving, so they really share a pool of tokens. And as I said, those of you who have extended packaging today already have the ability to make use of all of these products. And so now we're going to walk through in order Isight, Tosca, and FE-Safe and how they've contributed to developing this brake rotor. So beginning with Isight, in this part of the development, what we're going to do is look at the brake rotor, the brake disc, the outer portion of it. We're going to use Abaqus to basically do all of our simulation. And so we've developed a model of this within Abaqus CAE. Some of the components, we have a carrier that essentially supports the disk and is essentially attached to the wheel. And then also notable is the fact that there are 5 buttons that actually are the only way that the disk is attached to the carrier, and that's to allow for thermal expansion differences between the 2 pieces. All of the torque is transmitted through there, so we do have the contact is an important part of that to provide the torque transmission and really to secure the pieces. So we have that is an important part of our design consideration. The brake pads are what's producing the drag on the disk to slow the bike down. And so we, in running the simulation within Abaqus, what you will see is that we have switched the frame of reference, whereas normally the pads would be held still and the wheel and disc and carrier would rotate. In order to visualize easier, we're going to actually change the frame of reference to the disc and carrier so it appears that the pads are actually rotating around the system. So you'll see that throughout this presentation. It's really just so that it's easier to see the results of the simulations. So anyways, in the upper right corner you see a structural model of this, and it's showing the asymmetrical loading that's occurring. And then we're also looking at the vent holes and doing a thermal simulation because we're also very concerned about the performance of the disk. We'll study that in more detail. Now, what we would like to do is to be able to look at many different variations of this design very quickly and efficiently. So we've created a Python script that will automatically create the model within Abaqus CAE. A fairly common way to do this would be to just manually go in and create this disk in Abaqus CAE and then use the replay file as a starting point for your script. Once we have the script in place, we're ready to essentially automatically generate a structural model and a thermal model by running that script. We can run it multiple times and look at different designs in 3-button, 5-button, 6-button. We can really look at any number of designs that we want. So we've essentially built the foundation for automating this process. And so now we will employ Isight together with our script in the Abaqus CAE interface to begin to automate this process. So where we have the Python script that defines the model and Abaqus CAE to create the model, we're going to bring these into Isight and simply replace the Python script with the update Python script component in Isight and Abaqus CAE with the run Abaqus analysis component within Isight. And then we simply bundle that into a task, an automated task within Isight, and that essentially allows us to automatically generate all the designs that we need. So that can just essentially, without user input, we can just generate any multitude of designs that we need. But we want to have a little bit of intelligence incorporated into this design process. And so we're going to use the optimization algorithms within Isight. I think it would be easy for people to say, well, why do we really need optimization? We don't really need optimization. But the purpose that serves is to help us to balance some of these competing objectives. for instance, in terms of mechanical requirements, we want it low cost and low weight, but if we go too thin, we risk having a disc that's going to warp or fail prematurely. If we make it too thick, it is heavy, more costly, and not an attractive design from that standpoint. So we have this delicate balance that we need to strike, and we can use the optimization algorithms to find that perfect balance. In terms of thermal requirements, we have similar problems. We need to look at how do we best configure the holes, how do we meet the objectives that we need for the design from a thermal standpoint. So we have really the ability to look at both the mechanical and thermal requirements as we develop the design. With the mechanical requirements and the thermal requirements in mind, we can start to look at different variations of the geometry. We can look at different size for the holes. We can look at a different number of holes. We can look at a different pattern or position for the holes. And so we have these many, many different possibilities that we have to sort through. And very quickly it becomes a challenge to manage all of that information manually, both really from a file management standpoint, but just in terms of just keeping track of results, things of that nature. So what we're going to do is we're going to introduce our automated process and simply replace the task component with an optimization component. It's very, very simple to essentially turn that automated process into an optimization algorithm that will essentially move the design into a direction where we have improved both mechanical and thermal functionality of the design. So what we do is use that to automatically drive through a number of different designs where we're now looking at results from different hole size, pattern, number, different thicknesses, and all different variables of the design. And then after we've really produced a number of designs, run through the analyses, we want to be able to quickly identify which of the designs is our best option. And so Isight gives us many different ways and tools to be able to post-process that information. For example, in the correlation table that we see here, we're able to look at the way that the number of holes correlates with cooling area. And what we see is a positive correlation here, basically saying that as we increase the number of holes, we increase the cooling area, and that's a favorable trend. But if we look at the number of holes versus break area, we have a negative correlation, which is understandable. Basically, as we increase the number of holes, we reduce the breaking area. And so we have these competing objectives that we have to make sense of. And so we actually look to a different type of post-processing within Isight to help us further, and that's a scatter plot. So in this scatter plot of all of the various designs that were considered in the design process, we can look at the break area on the y-axis and the cooling area on the x-axis, and we can then look at different regions of this plot and rule out all of the lower points that represent insufficient break area. And after removing those points, we're very quickly able to find the optimum point where we have acceptable break area and we have the maximum cooling area. in terms of the thermal optimization, what we're interested in is understanding how the various different design configurations work from a cooling standpoint. After the brake is applied, the disc heats up. If we allow it to cool down, we look at the results after 15 seconds to really study the difference between the two designs. And what we see is in the reference design that was originally recommended by the designer, we have points of high temperature, whereas those corresponding points in the optimized design are significantly lower temperature. We also have local hotspots in the reference design which will contribute to warping and have other undesirable effects, whereas in the optimized we have much more homogeneous distribution of temperature. In summary, by taking advantage of the optimization algorithms and searching through many different designs, we were able to drop the maximum temperature by 30 degrees centigrade while maintaining sufficient braking area. So these are the types of things that we can do by using the optimization algorithms coupled with process automation that can go through many, many design increments at the same time. So this is the brute force method that that the computer can employ. It can just look at everything and find the best option. So now I'd like to move on to the process that we used to come up with the carrier design. And we used Tosca for that. So what we know at this point is that we have an optimized brake disc. We just went through that. We chose the 5-button design was the best design there. And we know that we have the carrier connected to the wheel at certain locations in the center. And we also understand our loading that's coming in through the brake pads and the brake disc. And so then what's left over really is this space in between the two, this design space that's essentially what we have to work within to come up with a carrier design. And for that we're going to use Tosca and employ a technique called topological optimization. And that essentially uses simulation technology, the machine part of it, where it has algorithms that essentially in a very smart way can find designs that are very efficient in terms of using stiffness and stress well, but that's combined with the engineer's input that has essentially set up all the boundary conditions and gives us the real estate available for the optimization to occur in. So it's really a good picture of collaboration between the man and machine here. We'll take that into Abaqus CAE to set up this optimization, and that task essentially consists of specifying the design space that we have to work with, and then we also define the objective. What are we trying to accomplish in this optimization? And here what we'd like to do is maximize our global stiffness, and our constraint that we're also looking at is to reduce the mass and to essentially make this a lightweight component. But at the same time, we're also able to impose other restrictions within the optimization process to make sure that we have cyclic symmetry in this case, or also to make sure that this is going to be manufacturable through a stamping process. So we have the ability to impose these other manufacturing and design restrictions in the process as well. Once we have that set up and begin to run the analysis, that's when really kind of the magic happens. what Tosca does is it essentially looks for material within that design space which is not being utilized and simply removes that material. And it results in the shape that you see here that initially is not what we probably would have come up with in our minds, but after reflecting on it, you start to realize that, yeah, that really does make sense. And that's really a common occurrence with topological optimization, that after the fact, yeah, it makes sense. I get it, but it's rarely what you would have imagined ahead of time. And that's really the power of Tosca and topological optimization. So basically what we've done here is we've taken and moved away from sort of the traditional design for that carrier. We've used Tosca to come up with this novel design based on algorithms that really make strong use of the material, and the result of that was a weight reduction of 30%, and at the same time it's actually twice as stiff as what the original design was. So we've really demonstrated good power of the algorithm here. Now, one thing I want to point out is that with Tosca, the optimization is based on nonlinear results. So the simulation behind the scenes is fully nonlinear analysis, and that's critical because that allows you to respect the difference between tension and compression. There is no way to carry tension between the button and the carrier, and it's important that we respect that in this situation, because when we use linear results, we're basically tying the two together, and as you might imagine, it then relies on tension between the carrier and the button, and that's just not realistic. So it's critical that you have the opportunity to use nonlinear capabilities within your development of a design, especially where contact is involved or any large displacements. It's really the same thing as choosing to use nonlinear analysis in any simulation versus linear analysis. You understand the limitations of linear analysis. Well, those apply equally true to topological optimization. And then finally, we also have a design that we know that we can produce from a stamping process. So we've heated that as well. So just sort of a review, we essentially started with a design space. We said this is the real estate that we have to work with. We used Tosca to then come up with the design based on a stiffness, but we're not done yet, because what we want to do now is continue to look at the detailed design and begin to make sure that we have not only the right stiffness, we want to make sure that we have a durable design as well. So that kind of takes us into the next step of the process, which is where we're going to use FE Safe in order to do a durability assessment of the design. And actually, it's even better than that. We're going to use Tosca in combination with FE Safe. But let's first talk about durability. What we're shooting for here is to make sure that we have products that have the life that our customers expect, that we have quality. We want to be able to minimize the warranty claims that we have. We want to make sure that we can have a design that's robust under any number of conditions, and so that really points to doing a fatigue assessment of your designs. Now, an important thing to note is that fatigue is the result of a local stress value, and so this is where shape optimization really becomes a critical part of the life prediction process. And so as we predict life, there are a number of different factors that we have to bear in mind. First is that for this brake rotor, for example, the motorcycle is going to spend its days, some days on the highways, some days on country roads, other days on city streets, and those all contribute to the fatigue of the part in a different way, and we need to take that into account as we try to predict life of this component. And then we also may take this to the track only a couple times a year, but those are very damaging. Those few events have such significant loading that those also have to be considered in predicting the overall life of the part. And then, of course, there's also the impact that other non-intended use might have on it, and they're again trying to contain warranty costs. It's something that we want to take into consideration. And then we also have touring bikes, or we have sport bikes, and we have different types of customers, and the way that they ride will have an impact on the life of the parts. We want to be able to use that information to essentially understand what the service life should be given any of these different conditions for different riders, for different uses. We can essentially use FE-Safe as a tool to help us make estimations of the service life that we should expect from that product under those circumstances. So in the brake rotor, what we've done is we've combined FE-Safe, so the fatigue life prediction tool, with Tosca Shape Optimization. And so let me pause for just a second and point out that we've really employed or talked about 3 different types of optimization today. And so let me just kind of revisit that. The first was Isight we used with parametric optimization. That means that we had design parameters. Those might be fillet radii, thicknesses, geometric parameters, or it might be thickness or material constants or anything that is a specific number that is in the design. We can adjust that. That's parametric optimization. And then we also used topological optimization that we saw in Tosca in designing the carrier. And that's essentially where it's a free-form design that's essentially looking for unused material and removing that from the design. So that's the second form of optimization. And the third form here, shape optimization, is now going to look at specifically just the surface, because fatigue typically is initiated at the surface, stresses at the surface. So we're going to look at the surface, make very modest changes to the profile of the surface in an attempt to enhance the life of the part. So that's really a very nice partnering of the fatigue prediction capabilities of FE-Safe with the shape optimization capabilities of Tosca. So we've looked at the carrier design now using shape optimization to try to reduce stress concentrations, and in doing that we've come up with the new optimized design, and it is almost hard to see the difference in shape. In the upper right hand figure you see the black and red, the black is the original profile, the red is the optimized profile, and so even with these very minor changes to the shape, we recognize a 300+% improvement in the life of this part. And so that's really why shape optimization is so important, because with very small changes you can dramatically improve the life and durability of your parts. And so that's a process that FE-Safe and Tosca work together very well with to to really drive innovative designs for you. So just to wrap up, in summary, we talked about how Abaqus is the core, the foundation. It provides the realistic simulation, the accurate physics behind everything. So I think we're all very familiar with that. But we also looked at Isight, which is what provides the process automation and the process integration, and it also allows us to do parametric optimization. And then we looked at Tosca, which drove the topological optimization of the carrier for us, gave us this unique star-shaped design. And we also used it to help us with shape optimization to improve the durability of the design, and it did that in conjunction with FE-Safe, which was providing the life prediction for all of the design variations that we looked at. So that's really kind of an overview: Abaqus, Isight, Tosca, FE-Safe. They've all four contributed to this innovative design process, and they're also all available to you, accessible to all of you that have the extended packaging today. So that's really kind of the story of moving from validate to innovate. And as I said, key is to tap into the computer, the power of the computer. Make use of that. Be the IBM Deep Blue computer beating Gary Kasparov. Innovation comes by employing that power and actually using it in the design process. That's really a necessary part of innovation. And so with that, I'd like to thank you for your attention, and I'll pass it back to Katie for a little bit of wrap-up, and then we'll go on to questions.
Great. Thank you, David. I'm just going to go over a few quick reminders and some information before we go ahead with the Q&A. So the eSeminar replay for this session will probably be released in the next week or so. So watch your email. We'll be sending emails out with details. And don't miss the other eSeminars that are in this Power of the SIMULIA Portfolio series. And you can find those and all of our upcoming eSeminars from the SIMULIA homepage at 3ds.com/Simulia. We also have all of our previous eSeminars on additive manufacturing and other topics on 3ds.com/SLC on our SIMULIA learning community. And you can register for future training classes at 3ds.com/SIMULIA training. And we're on social media. We'd love to connect with you and hear from you. So we're on YouTube, LinkedIn, Twitter, and Facebook. And with that, I think we're going to answer some, well, we've got one question that came in. So, David, the question is, any case histories in the mineral processing machinery, grinders, pumps?
Oh, boy. You know, offhand, I know I can picture some of the cartoons that we've created showing material handling, but in terms of actual grinding, I'm not personally aware of any, but I'm also not in a position where I would see everything that goes on out there. I think if you want to send me a personal note, or what's the best way to get a hold of us? I'd be happy to try to investigate that a little bit further. If you want to get a hold of me, my email is dqs@3ds.com, and I can work with you to see if we can find anything. But offhand, I'm not familiar. That's kind of a specific topic.
Okay, there's another question that just came in. David, can you briefly mention POP, live events coming up in Houston, Dearborn, Minneapolis, and Toronto? Oh, this is from Deepak.
Yeah, right. So just to, as a little bit of a plug, we do have a number of different events that are actually, these are free events that we invite you in to our offices, and we will meet and discuss in much, much more detail some of these products. And they are based in Houston. We have an event coming up that's really focused a little bit more on the oil and gas industry. We have an event coming up in Dearborn that will largely be focused on a little bit more on the FE safe side of it. That'll be of interest, we think, to the automotive industry. And let me think. What was the third event? We have Dearborn, Houston. But these do come up periodically, and again, I think you can find those events are all advertised in the learning community, and hope you can join us for some of those. And again, it's a great opportunity to meet face-to-face and go into a lot more detail about questions you might have about the products.
There's no other questions that have come in. Maybe we can give everyone a few minutes to think about any questions they might have. If not, we can wrap up a little early.
While we're waiting, I'll just make one comment that I think about a lot on this topic, and that is that with all of the challenges that product designers face in trying to think about all of the options they have and all of the conditions that they have to consider, the risk is very high. And so what happens is we have designs that are almost always a variant of a previous design. And that's really, I think, one of the big goals that I have in promoting this technology is to try to move beyond that, because frankly, variation of a design is very safe, but it's not a breakthrough. And I believe that these tools can give you enough confidence to take those risks, come up with really radically game-changing designs, and still have confidence in the reliability of the products. And to me, that's innovation. That's the key of innovation, is being able to to step away from just variations of your old designs and come up with novel approaches and take those to market. So that's really the goal that I have in really promoting the technology.
So a couple of questions did come in. One is, how does it handle the mesh in the optimization?
So there are 3 different types of optimization here. So I'm not completely sure which you're referring to, but in parametric that's fairly straightforward because you're modifying the geometry and then it's meshing just using the traditional Abaqus CAE meshing tools. In the topological optimization, wow, boy, that's really fairly invisible to the user, and so that technique is a little bit different. It's maybe not super analogous, to just creating a straight Lagrangian mesh. So I think, you know, the specifics of what's under the covers and how that works, to be fair, I would need to get somebody that knows more about it than me to explain. So I can't help you there. I will say that with shape optimization, though, we're essentially morphing the nodes, the surface nodes, and then you know, really just in the mesh. So that's why that's so efficient, because it's very, very fast. It's really just essentially looking at a new profile for the surface, morphing the mesh, and smoothing. So it's a very, you know, effective process for coming up with and preserving good meshes. I hope that answers the question.
Okay, the other question that had come in was, is Python program needed in order to use Isight?
Python is not required, because you can use Isight with many different things that have nothing to do even with simulation. So you know, Isight is really a process automation tool, and so you just whatever tools you already have, it just connects those all together. Now Python, in the example of the brake rotor, we did use Python scripting, but that is definitely not a requirement. Many people use Isight to run design of experiments simulations, and for that you really those are things that you can do with no Python required. So in this instance, we did just to help generate the model in a pretty detailed model for efficiency's sake, but that's not a requirement.
Okay, I think that was the last question, so I think we can go ahead and, oh wait, one more came in. Can CFD be included in Isight?
Well, the answer is yes. The question is how, and I think that, for example, you know, Isight can be used with third-party codes, and so the you know, there's certainly no requirement that it be Abaqus CFD. When it comes down to what specific functionality is available, I think that those are the details that are important, and I think it really kind of is a more of a case-by-case basis that we'd have to talk about. So that question, I think I would probably refer you to your local sales rep so that they can get a technical person to talk with you about your specific applications to see if we can do what you're trying to accomplish.
Okay, I think that was the last question, so I think we can go ahead and close today's session. Thank you, David, for a great presentation, and thank you everyone for attending. Look forward to seeing you in another eSeminar.
Great. Thanks so much, everybody, and have a great rest of your day.